So I said, other than a person.
Did you join?
No, I should play baseball.
Softball.
Oh, I'm good.
Okay, check here, make sure I'm got everything lined up like I want to. All right, yesterday we spent some time talking about arithmetic series. Do you have any questions over an arithmetic series? Talked about a formula that we could use to find the sum of the first however many terms of an arithmetic sequence. That's what an arithmetic series is. All right. All right. Now, hearing no questions, then we are going to today and tomorrow we're going to talk a little bit about geometric sequences in series. It's another special type of sequence that we're going to investigate. We're going to talk about the sequence part today. We'll get to the portion that involves a series tomorrow. Okay. So we want to be able to find the terms of a geometric sequence, including geometric means. Geometric means we'll talk about tomorrow. The word mean is an average. And we'll focus on finding the sums of geometric series tomorrow. Okay, so we'll talk about sequences today, series tomorrow for the most part. All right, so this says Serena Williams was the winner out of 128 players who began the 2003 Wimbledon Ladies Singles Championship. Before some of you were, you guys were all 5 born, right? No, before some of you were born. You would have been. It's a long time ago is what I'm saying. It's outdated. All right, after each match, the winner continues to the next round and the loser is eliminated from the tournament. This means that after each round, you only have half the players remaining. Okay. So if you look at this number of players remaining after each round, you form a geometric sequence. All right, we started with 128 players. There were 64 matches. There were 64 winners, 64 losers. So there's 64 people that remain for the second round. In the second round, there was 32 matches and 32 people won and advanced. Okay. After that next round, there'd be 16 matches and there were 16 winners. Okay. Well, what we end up forming there is what's called a geometric sequence. Okay, the number of players remaining after each round can be modeled by a geometric sequence. In a geometric sequence, the ratio of successive terms is a constant called the common ratio. All right, so we let D be common difference. We're going to say R is our common ratio. All right, so instead of adding or subtracting to go from term to term, excuse me, we are going to be multiplying. All right, and one way we can find that ratio is we can divide successive terms. All right, 64 divided by 128, 32 divided by 64, 16 divided by 32. What would the next term be here? If I went to a sub 5, what would it be? How many players would be left after? Well, it's not complicated. It'd be 8, right? Yeah. Then you'd have 4, then you'd have 2, then you'd have 1 person that's a champion, right? Right. Same thing kind of happens in the NCAA tournament, right? That just got done for the men and women. It started with 64 teams, then there's 32, then there's 16, then there's 8, then there's 4, then there's 2, then there's 1. Yep. So it works its way down. There, here we start with more individuals than the NCAA tournament, but it's the same idea. Okay. All right. So that's what the number of players in each round would look like. And that ends up being what's called an exponential function. Okay. We said arithmetic sequences were linear functions. Geometric sequences form what's called an exponential function. We talked about those in chapter 4 back before Christmas. Okay, it's got that little curve to it. All right. And just as we had a general rule or different rules for finding terms of an arithmetic sequence, we have the same for a geometric sequence. All right. Now, the first thing we're going to look at is if we look at a sequence, we're going to try to figure out, is it, arithmetic or geometric? Now, not every sequence we look at is going to be arithmetic or geometric. There could be other patterns. Okay. So those are the main 2 that we look at, but there are other types of patterns. So we're going to look at this sequence right here and determine whether it's arithmetic or geometric, and it could be something else. What do you think, Devin? What's the pattern there? What's the next term going to be? Put a lot of pressure on the guy on a game day here. What do you think the next term would be? You don't know? Somebody want to help him? Grace, you want to help him?
I think he got it.
No, he doesn't have it. Somebody's going to say 72 over here.
I don't have it.
Is that right? What's the key?
It's much.
You're going to subtract 7. You see it now? Okay, that's fine. Right? First differences are all 7, so that would make that an arithmetic sequence, right? That would be what we talked about in section 4, or excuse me, section 3. You look at the ratios, those would be the ratios. They are not all the same. Okay, they're probably fairly close, but they're not exactly the same. So this would be arithmetic with a common difference of 7. Right? Arithmetic with a common difference of 7. I'm going to move this up here. Okay. All right, so the next term would be 72. What about here? Determine whether the sequence could be geometric or arithmetic, and if possible, we can find the common ratio or difference. There's definitely a pattern to this, but it doesn't appear to be either one of those, does it? There's no way it's arithmetic because we go down 90, right? We go down 90, we go down 30, we go down 45, okay? So it's not arithmetic, okay? If we try ratios, the ratios are 1/2, 1/3, 1/5, or 1/2, 1/3, 1/4, excuse me. So is there a pattern to it? The next one would be 1/5, wouldn't it? So there is a pattern, but it's not going to be arithmetic or geometric. Okay, it's neither one of those. All right, it's neither one of those. What do you think the next term would be there? It'd be what? 1/5 of 15, which would be 3, right? Yeah, so it would be 3. So there's a pattern. It's just not one of those two special ones we're talking about in chapter 9. Okay, there is a pattern to it. It's just not arithmetic or geometric. All right, what about this one? Determine whether the sequence could be arithmetic or geometric. Well, I look at that right away and I think there's no way it's arithmetic. Down 4, down 0.8, down what's that, 0.16. Okay. All right, so once again, try to see if it's arithmetic. Is there a common difference? No. Down 4, down 0.8, down 0.16. It's not arithmetic. But if we turn to ratios, and once again, instead of subtracting consecutive terms, we would divide them. 1 divided by 5 is 1/5. 0.2 divided by 1 is 1/5. And 0.04 divided by 0.2 is 1/5. So that makes this a geometric sequence. All right, that's the ones we're talking about now that are new. All right, these are new. These are going to be modeled by an exponential function. Okay, so common ratio versus a common difference. That's how we tell the difference between arithmetic and geometric sequences. All right, so this is definitely geometric. So it could be geometric with a common ratio of 1/5. It looks like it is. From everything we can tell, it is geometric. Okay, so once we've decided it's geometric, we're going to come up with some rules for terms. Okay, so each term in a geometric sequence is the product, multiplication, of the previous term in a common ratio. Here would be what our recursive rule would look like. All right, we haven't talked about recursive rules since before Easter, but remember, recursive means you're building a term off its previous term. All right, so this would say any term is the term before it times the ratio. Okay, any term is the term before it times that common ratio. All right, 5, if we take 5 times 1/5, we get 1. If we take 1 times 1/5, we get 0.2. All right, so you take the previous term. Now, I think I've mentioned in the past that recursive formulas or rules aren't great. Why have I said they're not great? They work, but why aren't they maybe the best option? All right, you guys have been in class here. Come on now. Why did I say recursive isn't really the best way to go? What's the problem with it?
If you're looking for too big of a term.
Yeah, if you're looking down the line, you have to find everything in between, right? Exactly. If I wanted to find it, if I go back here, if I wanted to find the 13th term here, would I basically have to find all 13 terms.
Yeah.
Yeah, and that's why it's not good. Okay, that's why it's not a good method. But it still works, and some sequences have to be defined recursively. Right? Fibonacci is one of them. Now, here's what might be more useful, and just like when we talked about in section 3, how we said one, the explicit rule or the general rule was most important. That's what this is right here. Right? This rule right here is probably the most important thing we're going to talk about in section today. Right? This is the general rule. Right? This is the general rule for a geometric sequence. Right? It's an exponential function. It says any term is the first term times r, common ratio, to the n minus 1 power. All right? Any term is the first term times r, common ratio, to the n minus 1 power. So for example, the previous one we had 5, 1, 0.2, it had 0.04. Right? We could make a general rule for that sequence, and the things we need to know is the first term, and we need to know the common ratio. Right? Just as for arithmetic, we needed the first term and the common difference, right? Here we need to know the first term and the common ratio. So if I wanted to come up with a rule to find the 13th term of this sequence, I could say any term is 5 times 1/5 to the n minus 1 power. Right? That would be the general rule or explicit rule that could generate terms of that sequence. Okay. All right. So hopefully you have Desmos out. What would the next term be here? What would be a sub 5? Well, it would be 5 times 1/5 to the 4th power, wouldn't it? What's that going to be? See if you can find that on Desmos. 5 times 1/5 to the 4th power. I think I know what it is, but I want you to see if you can find it.
0.008.
All right. 0.008. Are we getting that? I think that's right. I believe that's right. Okay. And that kind of looks like it matches up the pattern. Okay. Do you think the next term would be 0.00016? Yeah. So there's a pattern there, and we can see that. But this general rule is very important, going to be very important moving forward in section 4, both today and tomorrow. Okay. Questions on that? Now, another thing, just in case you don't want to work with fractions, our ratio, we could also write it as 0.2. Same thing, doesn't matter. Okay. Doesn't matter. If you want to write it as a decimal, that's fine. If it's an exact number, then that's fine. Fractions might be better if it's not a precise number. If it was 0.3 repeating, you'd want to use 1/3. Right. All right, so let's look at using that general rule here. This is find the 9th term of the geometric sequence. Now, hopefully you can see there is some type of pattern there. 3/4, then we have -3/8, 3/16, -3/32, 3/64. Okay. Well, if we want to find the 9th term, I sure as heck better find the first term, which I can just circle that one right there. But then we also need to find the ratio. Right? It told us it's a geometric sequence. We don't have to guess. We have to find the common ratio. And how can we find the common ratio? Okay. How can we find the common ratio? Well, how would you find the common difference if it was arithmetic? You take the second term, you take the second term and you subtract the first term from it, right? Instead of subtracting here, what are we going to do? We're going to divide, right? Yeah. If we take the second term divided by the first term, or the third divided by the second, or the fourth divided by the third, whatever, right? That will help us find that ratio. So -3/8 divided by 3/4 ends up being -1/2. And does that kind of match up with this? Is the denominator already twice as what it was before? Yeah. And the signs alternate, so it's a -1/2. All right, so we know our first term and we know our common ratio. That's really all we need to know to come up with our general rule. Okay, our first term is 3/4. Our common ratio is -1/2. Now, one thing I want to be careful with on this one specifically is that ratio. You're going to want to make sure you're very careful to put -1/2 in parentheses there. Okay, just a little reminder here. These two things really aren't the same, are they? All right, so be careful with that. If you have a ratio that's a negative, especially, you're going to want to protect it. Just protect your ratio with parentheses all the time. That'd be a good idea. All right, here, everything would be negative because it's going to take 1/2 to the 8th and then change it to the opposite. Here, things will alternate, and that's truly what we want. All right, that's truly what we want. So a sub 9 would be 3/4 times -1/2 to the 9 minus 1 power. Oops, sorry. Getting ahead of myself here. Which would be 3/4 times 1/2 to the -1/2, excuse me, to the 8th power. Which, what is that as a number? I don't know what it is. I open my book and probably see, but off the top of my head, looking at it, I don't know what that's going to be. Does anybody have that number figured out? Probably have it as a decimal, and that's okay. But remember, we could change it to a fraction. So once again, get used to computing some of these things. I think as a fraction, it's 3/1024. Does that sound right? Okay. Do we remember how to turn it into a fraction? Should be a little fraction bar on the side there. Okay. Did you get to work?
Yep.
Are you sure? You didn't look like you did right away. Second time you did, or did you get to work?
Yeah.
Okay.
I don't-
Right away you kind of went, oh, I saw that. Right. And once again, we can writing it as a fraction might be the best way to go. Okay. So once again, that explicit rule or general rule, whatever you want to call it, is very important. All right, here's another one. Find the 9th term of the geometric sequence. Once again, what do we need to know to build our rule? We need to know the first term, which we have. I can just circle that. And then we need to find our ratio. Well, I'm going to look here to find my ratio. Is the ratio 10? I'm just going to look where it's easier. Right? If I take the 5th term divided by the 4th, I get 10. Right? We could take the 2nd divided by the 1st, and we'd still get 10, right? But I just look right there, and I see 10. So our first term is 0.001, and our ratio is 10. All right. So we should be able to write our rule. Now, once again, they took the 2nd divided by the 1st. Doesn't matter. Okay, doesn't matter which way you find it. Okay, just have to take a term divided by the previous term to find the ratio. And if we know the first term is 0.01 and the ratio is 10, we're just going to basically plug those in to our general form. Okay. So we need to know our first term, which we have is 0.001, excuse me, and our common ratio is 10. So if we want to find the 9th term, we would just say a sub 9 is 0.001 times 10 to the 9 minus 1 power. And that's going to work out to be 100,000. Basically, that's moving the decimal like 8 places because we took 10 to the 8th power. And that's realistically what it would do. All right. So that general rule, which we have right here, it's very important to know how to use that. It's very important to know how to use that. And we're going to look at maybe another way to use it here in a few minutes. Okay. But the general rule, or once again, I might refer to it as the explicit rule, because that's really truly what it is also, is the best way to go. Right, that's the best way to go. And once again, I think that is located on the back side of your note sheet that I gave you at the beginning of chapter 9. Geometric sequence, about halfway down, it gives you that formula, which maybe you want to add something to it to better understand it, but that's entirely up to you. Okay. All right, questions so far? All right, so instead of adding to go from term to adding or subtracting, instead of a common difference, we have a common ratio. Now, just like when we were given two terms of a arithmetic sequence, we could find the common ratio and unlock all kinds of things about it. Same thing's true here. When given two terms of a sequence, be sure to consider, okay, positive and negative values for R when necessary, okay? So sometimes we got to make sure we're careful. The ratio could be negative, it could be positive, all right? But if we're given two terms of a sequence, that should unlock everything we need to know about the sequence. All right. Find the seventh term of the geometric sequence with the given terms. All right, so once again, this is geometric. Now, if we can find the ratio, we could work backwards to find the first term, and we could then find the seventh term relatively easily, right? I'm not saying it's easy to find the ratio, but that's the first thing we have to do, right? So here's what our general rule looks like. Now, we're going to use this in a little bit different way. I might say the fourth term, wouldn't that be the second term times the ratio to the 4 minus 2 power? Did we kind of do this with arithmetic also? Yeah. Okay. So I'm saying, you know, we know the second term and we know the fourth term. If I plug those values in, I'm just gonna have to do a little math to find my ratio. So 48 is going to be 768 R squared. Okay. Now, R squared will then be 48 over 768. And I don't know what that is. What is that? I'm not sure. 1/16? 0.0625. Can you turn it to a fraction? Maybe not there. Is it 1/16?
Yeah.
Okay, so it's 1/16, but you're not wrong. Okay, it's just going to be maybe a little bit nicer as a fraction. Maybe not, and it won't matter. Actually, it won't matter. So if R squared is 1/16 or 0.0625, how do we find the ratio then? How do we solve an equation with an R squared? What do we do? What do we do? Square root, yeah. And the square root of 1/16 is 1/4, and the square root over here, if you use the decimal, it would be 0.25. So I guess it wouldn't really matter, okay? It wouldn't really matter. 1/4 or 0.25, those are the same thing. Okay, those are the same things. All right? Stop there for a second and let that sink in. All right, so we're still using that general rule to help us. We got the ratio, excuse me, we got the ratio to be 1/4. Took a little more know-how, but we got there. Okay, any questions on that? All right, so I'm going to erase this stuff. Now, what have we developed? We developed that the ratio is 1/4. Well, now I need to figure out my first term. How can I find my first term from this second term? How can I go backwards? Instead of multiplying by 1/4, what should I multiply by to go backwards? What's that? Couldn't hear what you said. Yeah, we'd multiply by 4, wouldn't we? Yeah. If we're going backwards, wouldn't we multiply by 4? So our first term should be 4 times 768, which is what? I don't know what that is. 3,024? I don't know. Is that right? You guys have calculators, right? 3,024? What's that?
3,072.
Okay, I was 72. I'm going to make it better. There we go. 3072. So now we have everything we need. It took a little more time and know-how, but we have everything we need to find any term of this sequence, right? Because any term of this sequence should be the first term times our common ratio, whether you read it as 1/4 or 0.25, it doesn't matter, to the n minus 1 power, right? Once again, it took a little know-how to find that, but it all relied on this general rule we talked about, didn't it? That's very important, like I said, yesterday. So what would the seventh term be? See if you can use your Desmos or whatnot to find it. Oops, that's all right. Oh, that's all right. Give me a second here. All right, what did you say, Ms. Meyer?
0.75.
So you got 0.75. You guys agree with that? Yes or no? It should be 3/4, 0.75. Because what do we have to do? What do we basically have to do there? Plug in what? To find the seventh term, we're going to have to plug in 7 right there. So 3072 times 1/4 to the 6th power. That's where we get that 3/4 or 0.75, whatever. I mean, doesn't matter which way we say it. Okay. Just like, when Jaden said 0.0625, I said 1/16, they're the same thing. Doesn't matter. Okay. I think I generally like to work in fractions if possible, but if they're precise, it's not a big deal if we use decimals. All right. Questions? It's just a different kind of pattern, right? Different kind of pattern has a different kind of general rule because it's, kind of modeled by a different type of function. Okay. Now, just as we did with the arithmetic sequences, we'll review things a little bit tomorrow. Okay, we'll go over this, the applications here, how to use things, especially because all these sophomores are gone. But then we are going to get into talking about finding the sum of a geometric series, which is the sum of the terms of a geometric sequence, right? So I'll just be adding up all the terms. Not all the terms, a finite number of terms. All right, so here are some questions to work on for tomorrow. Like I said, tomorrow we will get into, actually that's wrong here, hold on here. Don't do fun. Do 19 to 28, that's wrong. My mistake. Okay. All right, as you're working, if you have questions, be sure to let me know.